Okay, you've definitely heard of the law of conservation of energy. We all learned it back in school, right? Energy can't be created or destroyed, it just changes form. Seems super simple. A ball drops, its potential energy turns into kinetic energy. Boom, done. But what if I told you there's a critical, absolutely essential detail in this law that almost everyone, from high school kids to university students, gets wrong?
And that just raises a really interesting question, doesn't it? Why is something so fundamental to physics, a rule that governs literally everything, so tricky to get right when you actually try to apply it? Well, let's dig in and figure that out.
And look, this isn't just a random guess. Researchers have looked into this, and the problem is huge. This study points out that most students just can't tell the difference between all the various forces at play. And that, right there, is the heart of the problem, because those forces determine whether the law even works in a given situation. That's what we're going to untangle today.
So, here's our game plan. We're going to see just how tricky this law can be, we'll quickly go over the basic equation we all know, and then look at when that rule completely breaks down. After that, we'll hit the big secret. It is all about the system. We'll explore why so many of us get it wrong, and finally, how you can start to think about these problems like a physicist.
All right, first things first, let's just put a number on how widespread this confusion really is.
So check out this data. One study found that only about 37% of high school students could actually apply the law of energy conservation correctly. Now, yeah, it gets better in college, jumping up to 73%. But hold on. That means more than a quarter of university physics students still get it wrong. This is clearly not some easy beginner-level concept to really master. Okay, so if we want to figure out where things go off the rails, let's just go back to square one. What's the basic idea that gets taught in every classroom? Well, it all starts with this idea of mechanical energy, and that's really just a fancy term for the sum of two things. Kinetic energy, that's the energy something has when it's moving, and potential energy, which is basically stored energy, like the energy a rock has just because it's at the top of a hill. Simple formula, E equals K plus U. And in a perfect, sanitized textbook world, this total amount of mechanical energy never changes. The classic example is a simple pendulum, swinging back and forth in a total vacuum where there's no air resistance or friction to mess things up. And you can see how that energy just perfectly transforms. At the very top of its swing, it's all potential energy, just waiting. As it swings down, that potential energy converts into kinetic energy, hitting maximum speed at the bottom. The total amount of energy? It stays exactly the same the whole time. It's a perfect, neat, closed loop. But here's the big twist. The real world isn't a perfect vacuum. It's messy. And this is where that simple, beautiful rule starts to get complicated, because you have other forces showing up to the party. To really get this, we need to know about two different flavors of forces. First, you've got conservative forces, like gravity. With gravity, the work it does gets stored as potential energy. It doesn't matter if you lift a box straight up or take a long, winding ramp, the potential energy you give it is the same. But then you have non-conservative forces, like friction and air resistance. With these guys, the energy they take away is just gone. It turns into heat, and you can't get it back. The longer the path, the more energy you lose. Collisions are an awesome way to see this in action. In a perfect elastic collision, think two billiard balls hitting, they bounce off and the total kinetic energy is conserved. But in an inelastic collision, where things stick together, a bunch of that kinetic energy is not conserved. It gets converted into sound, heat, and the energy it took to bend the metal. And here's the kicker. These non-conservative forces are what change the total mechanical energy in a system. I mean, look at this example. A 15-kilogram panel falls from a helicopter. By the time it hits the ground, it's lost a whopping 130 kilojoules of mechanical energy just to air resistance. That energy didn't just disappear, of course. It turned into heat, warming up both the panel and the air around it. So is that it? The whole secret is just to watch out for friction? Well, not quite. This is where we get to the single most important and easily the most overlooked part of getting this law right every single time. See, what researchers have found again and again is that the biggest mistake students make is that they don't realize the law's usefulness depends entirely on how you define your system. So what in the world does that mean? Let's just use a falling apple. It makes this super clear. Okay, what if you define your system as just the apple? If you do that, then the force of gravity is coming from the Earth, which is outside your system. It's an external force. And that external force does work on the apple, making it go faster, so the apple's mechanical energy is not conserved. But
What if you change your mind? What if you define your system as the apple and the earth together? Well, now all of a sudden gravity is a force between two objects inside your system. It's an internal force. And with no external forces doing work, the total mechanical energy of the apple-earth system is conserved. It's the same apple falling, but whether the law applies depends entirely on how you decide to look at it.
Okay, so now we can really start to see why this is so tricky. It's not just one little thing. It's a whole bunch of related ideas that trip us up. The research really zeroes in on these specific stumbling blocks. We have trouble drawing a clear line between our system and everything else. We get confused about what's an internal versus an external force. We forget to look for those non-conservative forces like friction. And sometimes we don't realize that the law might work for one part of a problem but not another. And here's the real trap, the one set by how we're often taught. In class, we get fed a diet of perfect, idealized problems where energy conservation is always the answer. We do enough of them and we start to get a feel for it. But that's not real understanding. That's just pattern recognition. And the second we're faced with a real-world problem where the law doesn't apply, our intuition completely fails us because we were never taught the rules of the road for when to use this tool and, just as importantly, when to leave it in the toolbox. All right, so how do we fix this? How do we build a reliable strategy that lets us tackle any energy problem with confidence? Well, physicists use a kind of mental checklist. Step 1, and this is the most important one, you have to explicitly choose your system. Step 2, list out every single force acting on that system. Step 3, for any force that's doing work, figure out if it's conservative or non-conservative. And finally, step 4, now you can choose the right tool for the job. If it's just internal conservative forces, you're good to go with conservation of mechanical energy. But if you have external forces or non-conservative forces mucking things up, you have to account for the work they do. And honestly, of all those steps, that first one is the whole enchilada. Your choice of system is what determines which forces are internal or external, and that determines whether mechanical energy is conserved. You get that first step right, and the rest of the problem just falls into place so much more easily. At the end of the day, the law of conservation of energy for the entire universe is always true. Energy is never really lost. The real question for any given problem is whether it stays as useful mechanical energy. And the answer to that always depends on whether you're looking at the whole picture, at the right system. So the next time you look at a physics problem involving energy, the very first question you should ask yourself is, what exactly is my system?